Great. I think we're all set. Hello, everyone. Thank you for coming to my talk, especially people in Europe. I know it's Friday afternoon, so I really appreciate you being here. So today I'm going to talk about work I did recently with fellow Quantum Tinkerer members, so Chunchao Liu, Piotr Hojek, Tomasz Rozdal, and Michal Wimmer. And the name of the paper is Conductance, Asymmetry, in Mesoscopic Superconducting Devices due to finite bias. And you can check it out on arXiv. Also, the code is available if you're interested on Zenodo, and we have links in the preprint. So the mechanism that I'm going to talk about is, in principle, applies to any tunneling conductance experiment with a gate-defined tunnel barrier, but we choose to focus in our paper in Majorana devices, in particular nanowires. So I'm going to start with a brief recap of how Majorana signatures relate to conductance experiments. And I know that some of you in the participant list, I was checking it out, probably already very familiar with this stuff, so I promise not to spend too much time here. But so just a brief recap. We know that if we start from a simple tight binding model of proximatized nanowire, and we apply a magnetic field, eventually, if we make the field strong enough, we get to a point where we drive a topological phase transition and we have Majorana bound states. And in practice, what that looks like, if we plot the spectrum of the system as a function of the magnetic field, we kind of expect to see two states coming down from the continuum, quasiparticle continuum, and merging at the topological phase transition to form Majoranas. And so this is kind of a signature that people try to probe in experiments as well. And the way to do that in an experiment is, so the goal is to measure the density of states somehow. And one way to do that is to attach our proximatized nanowire to a normal lead, a bias voltage bias normal lead, through a tunnel barrier. And this is a tunnel barrier that we can apply through, for example, by setting up a gate here and applying an electrostatic potential. Now, the trick here is if I make this potential high enough, the conductance will be proportional to the density of states in the wire. And so if you've looked at Majorana papers once or twice, for sure you've seen this sort of conductance map where people in one axis have voltage, and here the voltage, you can kind of think of it as just energy. And on the horizontal axis, you'll see a magnetic field. And so in many of these papers, you'll see two conductance peaks, so two states coming down and merging at zero energy. And if the device is nice enough, they'll even have quantized conductance of 2e squared over h. So just like the model predicts. Of course, there's a whole there's a lot of discussion in the literature of whether this is sufficient evidence of Majoranas, but I won't get into any of that. I'm not concerned about that question here. The question I want to ask is this. So we know that the spectrum of this model is particle-hole symmetric, meaning that if I have a state at energy E, I also have a state at energy minus E. And we know that this conductance kind of reflects the density of states of the system. So is the conductance also particle-hole symmetric? Meaning, if I have a conductance at V, do I have the same conductance at minus V? And the answer is yes, provided that some assumptions hold. So first of all, this relationship would only hold at subgap conductances. So if I'm looking at subgap conductances, there's a chance it is symmetric. And I have the following assumptions have to hold. First, the scattering matrix has to be unitary. And that's also the reason why we have to look at subgap energies, because if we're probing energies above the superconducting gap, there are quasiparticle modes that can drain current away, and we lose the unitarity of the scattering matrix. And the other thing is that we cannot have dissipation, for example, coupling to some fermionic bath, some gapless normal region or something like that. So we have to have a dissipationless system. So that's one assumption. The second assumption is perhaps the weakest assumption of this set. It's that we have particle hole symmetry. This, in a sense, is if the interactions are negligible in the system, then this is an exact symmetry. So as long as the mean field Bogoliubov of the Gen picture applies, this is an exact symmetry. And thirdly, and this is the assumption that we're going to be looking at, we assume our system is in the linear response limit. And that means in practice that we assume that the system doesn't change with the applied voltage. Or more mathematically, it means that the dependence of the bias or the dependence of the Hamiltonian on the bias voltage is negligible. So if these assumptions hold, I get conductance plots that look like this. So on the top plot, I'm showing you a theoretical calculation of conductance. And on the bottom plot, I'm showing you the asymmetry. And the dashed line, it's maybe a little bit hard to see, but this dashed line is the bulk gap. And we're going through a topological phase transition, so it closes and reopens. And you see that below this line, there's no asymmetry. It's completely symmetric. So provided these things hold, we have symmetric conductance. And so now the next natural question is, do we see this in experiments? And the answer is not always. So there are definitely experimental data where the conductances are nicely symmetric, but there's also many examples where they aren't. And so here I'm showing you 3 plots of 3 separate papers. I think 2 are from Delft, judging from the color map, and 1 is from Copenhagen. And you see, for example, here you have one state that has higher conductance than its particle hole partner. Here in this one, there's kind of a more kind of a different type of asymmetry where actually one state, even after crossing zero energy, always has a higher conductance. And finally here I think this is Copenhagen data, it's a little bit more subtle, but if you focus on the regions at the low magnetic field, you'll see that the peaks here at negative bias have higher conductance, and the peaks are also slightly wider. Okay, so what physical mechanisms can explain this discrepancy? We can look at our table of assumptions and see which of these assumptions we can start breaking with some plausible physical mechanism. And one of them, perhaps the simplest thing to do, is just to say that we have dissipation in the system, and that breaks the unitarity of the scattering matrix. So of course, any quantum system we build is never fully insulated. There's always some coupling to some environment, and so it's a very reasonable thing to just say there's dissipation in the system. So these are two works that look at that, and what they do actually to model this dissipation is to add an imaginary on-site term, which makes the Hamiltonian non-Hermitian. And so this is kind of a heuristic way of putting in dissipation in the system. And they observe, indeed, subgap conductance asymmetry. There's another interesting paper. This one is looking at SDM experiments, Shiba states, I think, if I recall correctly. And there they look at basically tunneling from, or relaxation from André bound states into the quasiparticle continuum. And they also find that this can cause particle hole asymmetry and conductance. Okay, so these are physically plausible mechanisms, but they come with a problem, namely that they rely on quasiparticle poisoning or dissipation. And this is, of course, bad if we want to build a qubit, because we want to be able to store information for arbitrarily long times. So we don't want dissipation in our system. And so this is kind of the starting point for this work, is the question, can we find another mechanism that causes this particle hole asymmetry that doesn't involve dissipation? Or if you want to put it in another way, is it the case that if I see asymmetry in my conductance, that's always bad news? That means that I have dissipation. And so again, we can look at the table here, and you see that one assumption that hasn't really been studied is linear response. And so what we're doing in this work is to actually go beyond linear response and to allow our system to have a voltage dependence. And that voltage dependence comes just from the fact that when we bias the normal lead, we apply some finite bias, and we know that our superconductor is grounded. So, somewhere in between the two, the voltage has to drop. And so we study a system where the voltage just drops across the barrier, and then see what happens to the conductance. Before I proceed, I also want to say that there is, while we were finishing up this work, we became aware of another work out of Maryland that also introduced a mechanism that can break particle-hole symmetry without quasiparticle poisoning. So in their paper, they looked at coupling of André bound states to a bosonic path. It can be, for example, a coupling to a phononic path, and that also breaks particle-hole symmetry and conductance, but does not change the parity of the superconductor. So, in principle, it doesn't cause problems for storing quantum information. So yeah, moving on to our kind of formalism that we used. So we are going to let our Hamiltonian depend on the applied bias voltage. So our Hamiltonian is going to be basically two terms, our H naught, kind of the Hamiltonian, if you want, that you're already used to, let's say the proximatized nanowire, but we're going to allow to have an electrostatic potential which depends on the applied bias voltage. Then we can use the Landauer-Bodecker formalism to compute the current in this system. And this is a formula that was worked out already in the 90s by Lesofich and other co-authors. And this is similar to how you compute the current in linear response, but you have to be careful to allow the amplitudes in this integral to depend on the bias and not just the energy. We can differentiate this expression with respect to the bias voltage to obtain a conductance. And we can, if we look at subgap voltages, actually we end up with a simpler expression that I'm showing here at the bottom. So the conductance splits into two terms. The first one we call like a linear response like term. That's because if we take the linear response limit and neglect the voltage dependence, this is the only term that survives. And then we have a second term, which we call an integral term, which has a smaller contribution. And there it involves an integral of a derivative of this amplitude. And this term also has some interesting consequences, but indeed this guy here has the dominant contribution. Okay, so before we proceed to looking at more complex models, we can take this formalism and use it to compute the conductance in a toy model. And the toy model that we look at is just a single subgap Andrea bound state at some energy E naught. So our Hamiltonian is just E naught tau Z. And then we can use a very handy formula called the Weidenmüller formula that allows us to compute the scattering matrix of the system. And it's a formula that depends on the energy, the Hamiltonian of the system we're tunneling into, and on some matrix W. And W is a matrix that parameterizes the coupling of the lead modes to the bound state. And these couplings here, the matrix has this form, and these couplings here, we let them depend on both the energy and the bias voltage. Okay, so we have this. We plug in our Hamiltonian here. We use our formula for the current to compute the current and then the conductance. It turns out that around close to resonance, the linear response term, so if you remember, we had two terms here. And first I'm looking at this one, which has the major contribution. This term reduces to a relatively simple form. So I'm showing two equations here, one at positive bias, another at negative bias. And so this is just a Lorentzian with height and width that depends on the tunneling rates. And one thing to mention here is that for just convenience of notation, I've hidden away the dependence of the energy and bias. But keep in mind that these things are dependent on energy and bias. And so that means that the height and the width of these peaks will be different at plus and minus voltage. But I'll show this more clearly. Let me walk you through some consequences of this formula. The first one is that if we set TE, so the tunneling electrons, to be TH of minus E and minus V bias, this would be the linear response limit, we recover symmetric conductance. So this is a plot I'm showing here where I have both the conductance and the tunneling rates. And if I obey the symmetry, then I recover particle-hole symmetric conductance. However, in general, this doesn't have to be the case. And so if I relax this assumption, I suddenly get peaks of different heights and width. And finally, the third thing that you see from this formula is that at zero bias and zero energy, particle-hole symmetry dictates that these couplings have to be the same, TE and TH. And what that implies is that as I move my resonance closer to zero energy, the asymmetry has to vanish. Or, maybe another more intuitive way to say this is that these effects have to scale somehow with the bias voltage. So it makes sense that as I decrease the bias, the asymmetry goes away. And so here I'm showing you the same plot as before, but I'm moving the resonance closer to zero energy, and you see that the width and height gradually become closer and closer to each other. All right. So finally, we can also compute the integral term. And to compute this, I obviously won't go through the math here, but the only assumption basically is that the tunneling rates vary slowly across the conductance resonance. And then we can obtain an expression for this term, which splits in two terms, one arctangent and one Lorentzian. And the key observation here is that both these terms vary on the same scale as the linear response term, so they have the same width parameter. And so that means that this term doesn't actually change the width of the peaks, but it can change their height. So what I'm plotting here is in orange, I'm plotting just the linear response-like term, and then in blue, both the conductance with both terms, and you see that the width remains the same, but the height of the peaks changes. The other important thing about this term is that it allows to have a negative differential conductance. So the other linear response-like term is always 0 or larger, but with this term allows to actually have a negative conductance. Okay, so these are the results of the toy model. We saw some interesting things. We can in principle have different height and width, and this effect ought to disappear as we get closer to zero energy. So what does this look like in a more realistic setting, in a more realistic model? So what we did is we took a 1D tight binding model of a topological nanowire, and we used a square barrier to couple the two, but we allow this barrier to have a linear voltage drop. So usually in linear response, there would be no voltage dependence on this barrier. Here we are saying when we apply a voltage, what happens is that we raise the band bottom on the left side, and then we drop the voltage linearly across the barrier. And the motivation for that is just that if you solve Laplace's equation with fixed boundary conditions at some voltage, this is what you would get. You'd get a linear voltage drop. This is kind of a zeroth order approximation of what the electrostatic profile could look like. Or this wouldn't be electrostatic, but yeah. Right. So we have a linear voltage drop. Additionally, we also put in a quantum dot potential. But this is not so much, the only reason we put it in is just because we want to have subgap Andreev bound states so that we get kind of a richer subgap spectrum that we can that we can then look at. All right, so I'll jump to the results. Here I'm showing you the results of the conductance in a nanowire with an induced gap of 0.25 MeV. So the left-hand side plot is the linear response plot, so neglecting any voltage dependence of the barrier, and the dashed lines denote the bulk gap. What you see is that the linear response is perfectly symmetric, as we had already seen in previous plots. But if I now move to the middle plot here, we are allowing the barrier to vary with voltage. And now we see that there's a clear asymmetry in the peaks here. And I'm plotting that plotting that explicitly on the right-hand side. And you see we have asymmetry below the bulk gap here. Great. The other thing we tried next is that these effects scale with voltages. So if we increase the induced gap, we have to look at higher voltages. So probably we would get a larger asymmetry. And indeed, that's the case. So I'm showing you again the same sort of configuration of plots: linear response, symmetric conductance, and a finite bias conductance here. And you see that the asymmetry is much more noticeable here in this case. So we expect that these effects become more prominent if we move to materials with higher superconducting gap. The next thing we looked at was how this asymmetry depends on the barrier shape, on the barrier parameters. Is this a thing that's basically like very fine-tuned, or how does it scale with the barrier shape, etc.? And so here what I'm showing you is the height asymmetry as a function of on the vertical axis we have the width of the barrier, and on the horizontal axis the height of the barrier. And I'm showing you a normalized okay, so basically I compute the conductance profile, I take the conductance height at resonance, and I look at the difference but normalized to the height. So relative asymmetry. And what we see is that the asymmetry goes down smoothly as we go to higher voltages, higher heights, or as we go to wider barriers. So as we move closer to the tunneling regime, the asymmetry vanishes. So this is kind of if you want, kind of a signature of this type of asymmetry. And the intuition is that if you have a higher barrier, then the voltage drop ought to matter less, relatively speaking. And also, if you have a very long barrier, then the linear voltage drop has a very small slope, so an electron tunneling through would not notice this slope. Okay, so asymmetry vanishes as we go deeper in the tunneling regime. The other thing we looked at is, are there other shapes of the barrier, so not just the square barrier, that can cause more asymmetry? And it turns out that if you use an mirror asymmetric barrier, you can increase this asymmetry. So here we're looking at in blue, the finite bias conductance for a square barrier, and in orange for a triangular barrier. And you see in particular in the shape that the peak gets more distorted and a bit wider when we have a triangular barrier. And we give, I won't get into this because I don't have much time, but we give an intuition for this in terms of the WKB formula in the paper if you're interested. All right. Finally, we also looked at 3 terminal devices. So now we were kind of looking at the traditional local conductance setup, but recently the field has kind of also been exploring these non-local conductance setups, where the advantage is that we can directly probe the bulk topological phase transition, and so in principle we can have unambiguous signatures of Majoranas. And so the setup is similar. You have a normal lead, approximatized nanowire, but then on the other side you attach another normal lead. Now, because electrons can now tunnel from one lead to another, even at subgap energies, that means that my scattering matrix is no longer unitary, right? So before, if I had an infinite nanowire, let's say, then there were no propagating modes below the superconducting gap. So everything that I sent in as an electron either had to be reflected as an electron or a hole. But in this case, it's possible that an electron comes in and just tunnels through the nanowire to the other lead and continues to propagate. So that means scattering matrix is no longer unitary, which in turn means that we no longer have particle-hole symmetric conductance, even if the barrier is not voltage dependent, even in the linear response regime. However, there are other symmetry relations. So in this type of system, the conductance is promoted to a matrix, because we now have more than one terminal. And the definition of that matrix is given by this formula. So we have I, the current in terminal I, a partial derivative with the voltage in terminal J. And it turns out that if we define the asymmetric part of G to be this this object here, this is actually exactly what I was plotting here. So just G of V minus G of minus V. So defining this object, it turns out that there's a very nice symmetry relation, that the asymmetric part of the non-local conductance is equal to the asymmetric part of the local conductance. And this was last year. This was kind of there were two back-to-back papers out of Copenhagen, one theory paper showing these relations, and an experimental paper measuring these relations in the actual device. And they found very good agreement, but some discrepancies from a perfect symmetry relation. And what we wondered was, well, okay, this derivation also assumes linear response. So could it be that by allowing a voltage dependence barrier, we can kind of get we can break the symmetry relations in a similar way to what they see in experiments. And so we extend our model to support two leads. So here we have again our voltage dependent barrier, and we have two quantum dot potentials, one on each side, again just to get a richer subgap spectrum. And we plotted the asymmetric part of local and non-local conductance. And what we see is indeed that the symmetry relation doesn't hold perfectly. So for example, if you look here on the local conductance, there's kind of a background conductance that we don't have in the non-local conductance. Or here in this peak, you see that this peak is different than here. So indeed, the finite bias effects do break this symmetry relation. But we are not able to reproduce one other feature in the experiment, and that is they observe that in the local conductance, they see an avoided crossing, whereas in the non-local conductance, they see an unavoided crossing. And that's not something that happens in our model. Of course, this is just a set of parameters. We cannot completely rule out that maybe in some parameters we would see this in our model, but in my experiments, I never saw anything like this feature. All right, so this brings me to the end of my talk. To summarize, I think our main message is that not all conductance asymmetries are bad news. A voltage drop across a tunnel barrier can also cause asymmetry without quasiparticle poisoning or dissipation. And our simulations show that this asymmetry can be in the range of 5 to 50%. And perhaps an interesting thing to look at is how this asymmetry behaves as a function of system parameters. And there we found kind of two signatures, if you want to call it that way, of this type of symmetry. One is that it typically increases with V bias. So at larger biases, we expect to see larger deviations, and it must vanish when the bias goes to 0. And then secondly, we observe that as we tune deeper in the tunneling regime, we should see this asymmetry also vanishing. In terms of things that we have left to do, we would like to get a more realistic model for the barrier, for example, by solving the self-consistent Schrödinger-Poisson equations. So that's an interesting extension. And also there are a couple of, there are some instances of conductance asymmetry that we cannot explain in our model. This is one that I showed before. So when you have a state which is always more, always has more conductance, this is not something that our model can explain. So this is likely some other type of mechanism. And that is the end of my talk. So thank you very much for listening, and happy to take any questions.
I have a question, André.
Yes.
Can you please show the comparison between your three-terminal simulation and the experimental data?
Mm-hmm.
So you said that the feature that you cannot explain is this avoided crossing versus the unavoided crossing.
Yeah, exactly.
But so do you know whether the states that the experiment sees are originating from the same end of their device or from the opposite ends? Could that be something relevant here?
I think they, if I remember correctly, and also somebody in the audience, if they remember, please chime in. I think they measure something to show that the states are. Okay, honestly, I don't want to make a wrong statement, so I don't remember. No.
All right, but okay.
Sorry, if I may, I think these states are from under the entire superconductor. They're short superconductors, so they couple to both sides.
I see.
So that could be a difference then.
Mm-hmm. That's a good point. Yeah.
Can I ask a question? Hi,
Sure.
Sorry, I have a question. So when you say that when you look at NS device, so only like normal lead in the superconductor, you say like below the gap there are no propagating modes, so there is no dissipation, and above gap there is. But what I don't understand is, like, if you allow for any propagating mode above the gap, finally it has to go to other lead, so the electron cannot disappear. So that makes me confused. How do the dissipation affect asymmetry? What is let's say more intuitive way? Because yeah, it's propagating, but it goes to the lead finally.
Yeah. So okay. So maybe I used the term dissipation a bit loosely there. What I mean is that above the gap you have modes that can drain current to the lead.
Yeah, but
below the gap, no.
But everything what you measure is finally measured because it's drained to the lead.
Sure. Okay. So below the gap you have Andreev reflection, so you can have electrons going into the condensate, but everything that you send in as an electron has to be reflected. Even if you have perfect Andreev reflection, you have to reflect as a whole. So that's why the scattering matrix is unitary. So that there, I was a bit imprecise there. Yes.
Okay, and because everything what I send above the gap is going to be, let's say, transmitted as electron.
Mm-hmm.
And what is there not unitary then?
Well, there you have like single particle modes that that can carry current, whereas below the gap you have Andreev reflection processes. So you go as an electron and you reflect as a whole, and that means that you can have a unitary scattering matrix. But if you're above the gap, you can just transmit, say, as an electron, and that means that your scattering matrix loses unitarity.
Yeah, I know, but where is the electron lost? Because finally what I see is the conductance. So that electron on the left becomes electron on the right, and it goes to the lead. So why do I end up with less of a conductance?
Sorry, you're talking about this setup or the two-terminal
two terminal. For
Okay,
this
so
setup, I understand, but for the two terminal, because finally everything that goes from the left goes to the right. So yeah, I find it difficult to understand in a more intuitive way. Like, where is this?
So I'm not saying that there is no current. I'm just saying that the scattering matrix is unitary.
Okay, so there is something that makes electrons to couple less to electrons than something that makes holes to couple the same amount to the holes.
No, no. I would just see if there's another way to explain it. So do you agree that below the gap there are no quasiparticle modes, right? So the only allowed process is Andreev reflection.
Yeah, that's fine.
Right. So that means that if you look at the reflection amplitudes, you can go in as an electron, but then you have reflection amplitude as a whole, right? And then you'll have a unitary reflection matrix.
Yeah.
But above the gap, you can have transmission of electrons, and so that means that your reflection matrix will no longer, sum to 1, so it will not be unitary.
Okay, but then this is going to be different from plus V bias and minus V bias. Let's say for V bias bigger than delta, and for minus V bias smaller than minus delta, that's going to be different.
In what sense different?
Like because we want to have a symmetry, so this means that somehow electrons that are sent from left to the right at plus V bias will transmit less than what the holes that are transmitted from right to the left at minus V bias.
Yes. So that could be the case. Yes, that's indeed what happens. Yeah, and that has to do just with the type of barrier that you have at plus and minus V bias.
Yeah, exactly. That's what I mean. Like, but then it sort of falls under the assumption that the barrier is different for electrons and holes.
Yes.
So that's sort of that can be explained by the barrier being different, not by existing of some modes coupling, or because finally everything is going to couple to something and is going to be drained to the superconductor.
So yes, I agree with you that this mechanism relies on having different barriers for electrons and holes, plus and minus V. Yes.
Okay. Yeah. Thanks.
No problem. More questions? Okay. In that case, I guess we are done. Unless
Thanks for the talk.
Yeah, no problem. Thanks everyone for coming once again.
Thank you.